Today we will be talking about model-free prediction and control, and I'll be covering quite a lot of material, and I will also get back to some of this in later lectures, especially when we're considering function approximation. And specifically, of course, we'll talk about deep neural networks at some point, but not yet during this lecture. Sorry, there we go. The main background material is Sutton and Barto chapters 5 and 6. And just to recap again, this is just the setting. This is the same slide you've seen now a couple of times, where we're interested in the science of making decisions, and especially in a sequential setting where we can interact with the world repeatedly. And to do that, we could either learn a policy, a value function, or a model. And in this lecture, we'll mostly be talking about value functions, similar to the previous lecture. In a later lecture, I will talk more about, for instance, how to learn policies directly. Okay. So the last lecture was about planning with dynamic programming. In this, we assumed we can observe and interact with the Markov decision process, but we don't really need to sample because we have access to the full model, so we can just plan. I say just plan. Of course, there's ways to do that that are more or less efficient, and there's lots wide literature on this topic. But it is somewhat of a limitation to have this assumption that you have access to the true model. So in this lecture, we'll be talking about methods that can learn without needing access to the true model, and therefore can learn directly from interaction with the environment. In particular, we'll be covering two distinct but related cases. One is model-free prediction, where the goal is to estimate values. This is called prediction because these values, as you will remember, are expected returns. And returns are something about the future. And therefore, a value has the semantics of being about the future. And this is why we call this prediction. We'll also talk about model-free control, but we'll limit ourselves to value-based methods for this lecture. In later lectures, we'll talk about methods that don't necessarily store values explicitly. And in model-free control, the goal is to optimize the value function and the policy. Again, model-free, so in an unknown Markov decision process. What we'll not yet cover, but will come in later lectures, is learning policies directly, as I said. Also, how to deal with continuous Markov decision processes and deep reinforcement learning. These last two are related. For this lecture, mostly we'll consider the tabular case, so we consider basically any state value or any state action value to be stored somewhere in a table, so we can just update it directly. That's not a strong limitation of the methods, but it's just for clarity that we'll consider that case extensively first, and this is also what is done in the Sutton and Barto book. But don't worry, we will not lean on this too heavily, and we'll later extend all of this to the case of arbitrary function approximation, including deep neural networks. Okay, so the idea here is to move towards sampling because we want to get rid of the assumption that we have a true model. And therefore, we want to use experience samples to learn. We call the direct sampling of complete episode trajectories Monte Carlo. Monte Carlo is a model-free method. We just sample. We need no knowledge of the Markov decision process. And we already saw a simple case of this when we discussed Bandits in the second lecture. Because there was no Markov decision process there, or if there was, it was a very simple one with only one state. But we were already doing something that is very close to other methods we'll discuss here. We were already sampling. We weren't assuming there was a model given. We were just going to sample these rewards, and we would average them. And this would give us good estimates of the action values for each of the actions. Now, there's two ways you could write that down. The top one there basically says we define an action value, Qt, which is an estimate of each action, as the sample average of the rewards. The notation is a bit verbose there, but the indicator function just means we sum over all time steps, but we're only actually looking at the time steps on which you took specifically this action. So a simpler way to think about that is just look at all the rewards you've seen for this action and you just average those. And then the assumption that this is a good thing to do is based on the fact that this sample average will, just due to the central limit theorem, approach the actual average reward, which is the thing that we're interested in. Now, equivalently, we can write this down as on the bottom, where we basically turn it into a step size algorithm, where we have a new reward, and we just update our estimate a little bit towards that reward. If you pick your step size specifically to be 1 over the number of times you've selected this specific action, then these two things are exactly equivalent. But this already points to maybe a more general setting, where we could also think about having, say, a constant step size to deal with non-stationarity, or maybe even towards the function approximation case, as we'll see later, in later lectures especially. Now, one thing to note is that I've changed notation slightly from the Bandit lecture. This is just to prevent confusion that I mentioned this, because conventionally in the Markov decision process literature, we denote the reward coming after the action at the next time step, because we consider the reward and the next state to arrive at the same time after you've taken the action. So we normally say you're in a state st, you take an action at, and then you observe a reward rt plus 1 and a state st plus 1. When we were first discussing Bandits, we had an action at time t and a reward at the same time t, which is also the convention in the literature. So this is just to know there's like a slight offset there, and unfortunately, both notations are common in the literature. So it's good just to be aware of that. In this case, we went to the MDP formulation because we'll be talking about the full sequential case. And this is just a special case where there's only one state. Now we can already generalize this slightly, just as a somewhat of a teaser of where we'll be going, and also to show that this is a more general method than it might seem at first. We can consider bandit problems where there's a certain context. So what we're essentially doing, we're not yet rolling in the sequentiality, but we are rolling in state in the sense that there's a certain context in which you take your action. Now we'll still consider at first here episodes that end after exactly one step. So you're in a state, you take an action, you get a reward, but your action doesn't impact the next state. In fact, the next state maybe just gets sampled from some independent distribution, and there, again, your goal is to pick an action, and so on. And we still want to estimate the expected reward, but this is now conditioned on the state and the action. Now the reason to put this here is to also show that this is still, in some sense, a fairly simple algorithm in the more general case. Even if your state space is really big, for instance, it's a continuous space, maybe it's, I don't know, pixels or some continuous sensory motor stream that you can observe, then you could still think about doing something like this, but you would maybe more naturally then minimize a loss, where you basically want this function to be the same as the rewards, and you just have this instantaneous loss down there, and then you can consider the total loss, for instance, to be summed over all samples that you've ever seen, and then you just want to minimize that. And this is just regression, essentially. So one way to estimate without using a model is just sample rewards and then estimate by regression. The sample average is just the simplest case of regression, where we assume we can store these things exactly in a table. But the idea is more general. Now this is like a small step into the function approximation land. I'll now mostly go back to the tabular case for the rest of the lecture, but we'll get back to the function approximation setting in much more depth in later lectures. But instead of going there, instead we're going to roll back in the sequentiality that we discussed in the previous lecture when we were discussing dynamic programming. So we could think of an easy algorithm, in some sense, to do policy evaluation. So the goal here, just to be clear, is to do policy evaluation, so we're interested in estimating the value of a certain policy. Later on I'll talk about how to optimize, but for now we're just doing the policy evaluation. And one way to do that is to sample a whole trajectory with that policy, and then to get a return. But note now that normally I have this return trailing off into the future without committing to a certain endpoint. But in order to get the full return, I need this to terminate at some point. So I've basically denoted here, there's a time step capital T, which is in the future, so it's somewhere beyond the small t. And this is the time step at which this episode ends. And this might be a random thing, this is why it's a capital. In some cases it might be deterministic. In the bandit case, this is always exactly at the next step, for instance. But we need the full return, so we're going to just sample a whole trajectory, a whole episode by executing that policy. And then we can do the same thing we did for the bandits, we can just average. And if we have a discrete MDP, where there's a limited number of states that you can just observe, you could, again, just store this in a table. You could just average per state and potentially per action if you want action values rather than state values. In a more general case, you could again do regression. This is called Monte Carlo policy evaluation, because we use Monte Carlo samples of the full trajectory of the return. Sorry, Monte Carlo samples of the return, using the full trajectories. And then we use this in this case to do policy evaluation. Is it clear so far? Again, always stop me whenever. Now, just to give you an example, that, well, it's more or less an example that this works in some sense. We can consider a simple case of a blackjack setting where there's 200 states. And these 200 states we're just going to represent separately in a big table. Well, it's not that big. And the state is composed of how many points you have right now. If you have fewer than 12 points, you'll just keep on getting cards until you get 12. So you'll always be in a situation where you have 12 to 21 points. And the goal here is to have more points than the dealer. The way this works with these playing cards is that all the, if you don't know blackjack, all the faced cards are worth 10. The ace is worth either 1 or 11, and you can pick whichever is most useful to you. And the numbered cards are all just worth their number. And you get dealt these cards from a deck, so you can't see what's coming up. And the dealer is only showing one of its cards. So the dealer shows you a little bit of what it already has, but not exactly. So that's the other part of their state, what the dealer shows, and this can either be an ace or it can be anything from 2 to 10. So that gives you 100 states, and then we separately encode basically the information of whether you have a usable ace, because that's not captured in that number from 12 to 21. So we need one additional bit of information to tell us whether there's an ace as one of these cards. And a usable ace means that you could still, you're using it now to represent 11, but you could still pick it to represent 1 later on, if you would so desire, which can be useful. Now this is just the game, which is, by the way, not that important. If you missed any of the details or you're confused about the game, it's not that important. We're just going to use it as an example. And there's just 2 actions. You can stick, which means you keep your current score, and then it's the dealer's turn. And then the dealer will basically deal itself cards according to some policy. And then at the end, you'll see whether you've won or not. Alternatively, you could draw, which means you get another card. But the risk is you go beyond 21, at which point you lose. That's denoted here at the end. The reward for a draw is -1 if your sum of cards goes beyond 21. And then the episode ends. And otherwise, the action is considered to be worth 0. And this is, excuse me. And the reward here is 0 because we're essentially aiming for the win. We're encoding each step during the episode as being worth 0, because eventually you're going to have to stick if you haven't terminated yet because you've went beyond 21. And when you stick, then the dealer will do its thing. And if you won, so if your sum of cards is higher than the sum of the dealer cards, you get +1. The same applies if the dealer would go beyond 21. In that case, you've also been considered to have won. If you have the same number of cards, in this case, we'll just define that to be 0. You could also define that in some cases the dealer wins a tiebreak. In that case, you would have a -1 there. But in this case, we've defined it to be 0. And you get a -1 if the dealer has basically more points than you do. Now, to me, it's not immediately obvious what the values are of a certain policy. But you could define a policy. And then you could just check by running Monte Carlo. And that's what we did. Or essentially, this is from the books. It's not what I did. But what this shows is the whole state space. So the 2 flat axes are essentially whether how many points you have, how many points the dealer has. And then it's split out into 2 planes, depending on whether you have a usable ace or not. So there's in total 200 states there in basically the column on the left. And there's again 200 states here in the column on the right. The difference is that we ran more learning episodes essentially here on the right. And you see that at some point it becomes very stable because we're just averaging. So by the law of large numbers, the variance of the estimate goes down. And at some point you get a fairly reliable estimate of the quality of your policy. Now this example is in the book, so you can go through it again at leisure if you want. But the pointer is just to show that you can find these solutions, that it works. And that these solutions might also look there's a little bit of interesting structure here that you might not immediately be obvious just by looking at the problem. So that was just an example of using Monte Carlo policy evaluation. But it's not the only algorithm you can use, and it's not always the best algorithm. I mean, this is a fairly small problem, and we already needed to generate 500,000 episodes to get very smooth functions. So what we'll consider here is something more akin to the dynamic programming we discussed last lecture. The top two equations here are the same as what you've seen last lecture. The first one is just the Bellman equation. That's a definition. That's the definition of the value that we want to estimate. The second one is policy evaluation with dynamic programming, which you've seen last lecture, which basically just turns this first equation into an update. And as we've discussed, this will converge to the same values eventually. But you need a model to do that. You need to be able to roll out this one step. Now, alternatively, this is just an expectation that we can sample. So a naive thing to do is just to sample this thing and then to plug that in as a new estimate. That's typically not such a good idea because this will be noisy. There might be noise in terms of the reward, there might be noise in terms of the next state, and therefore it's not immediately obvious, and typically it won't be the case that this is a better estimate than the previous one. It might be just more noisy than the previous one. So what's better is to average this target. So essentially what we're doing is something very similar to before, but instead of using the Monte Carlo return, we're going to use this one step and then bootstrapping on an estimate value as a stand-in for the actual value. There's multiple ways to interpret it. One way to interpret it is as an approximation, a sample-based version of the dynamic programming algorithm that we have right there. A different way to interpret this is to see this as a return estimate where we've taken one real step and then we just replace the rest of the sampled return with this estimate that we already had at the next state. But because we use a real sample, it's a little bit better in a sense than if we didn't do that one step. This is called temporal difference learning. And the reason essentially is because you can interpret this whole part between the brackets. You can interpret as an error between your current value and the target. And it's an error in the sense of a one-step temporal difference. So this is called a temporal difference error. And then this is called temporal difference learning. So to recap, in approximate dynamic programming, we used one step of the model and bootstrapped. I put approximate here in brackets because you could apply these same ideas to construct a target and then to have a parametric function that updates towards the target rather than the full tabular thing that we looked at the previous slide. And in Monte Carlo, we could just sample the full return. We could use that. And the idea of TD learning is basically to combine these two things. We both sample, but we also still bootstrap, which means we use an estimate at the next state value. Now the first target here is an approximation of the real return because we bootstrap. We're not guaranteed that the value at iteration k, at the previous update essentially, we're not guaranteed that this is going to be the same as the expected return from that point onward. But that's the only approximation. We are using the real model, so for the rest there's no sampling error. Conversely, in Monte Carlo, there's no approximation error due to bootstrapping. We're not using any estimates. This is an unbiased sample for the actual value of that policy, but we do get sampling error. We just get a little bit of noise in some sense. Now, TD learning basically gets both of these. We're approximating in both of these ways. However, it turns out there's less noise than in Monte Carlo, and you don't need reliance on the model that you do in dynamic programming, and this tends to work quite well in practice. So this is called, using this as a target is called temporal difference learning. And this is a very central idea in reinforcement learning, and it's basically used all over the place, so it's important to understand. Now this has a couple of properties. As I said, it's model free, so you don't require any knowledge of the Markov decision process. And it can also learn from incomplete episodes due to the bootstrapping. This is something that may have not been immediately obvious, but for the Monte Carlo return, we needed to sample the whole trajectory, we needed the whole return. But if your episodes are really, really long, it might take a really long time for you to learn. And in some specific cases, you could even have a policy right now that just loops somewhere. Like a robot that goes into a corner and bangs its head against the corner because it has a poorly learned policy so far. And if the episode never really terminates, then learning would never happen. Whereas in temporal difference learning, you could update after each and every transition, which means you can sometimes learn much faster. Yes? Sorry? Yes, sorry. I should have been probably clearer about that earlier on. An episode is basically a chunk of experience where at the end of the episode, you reach a terminal state. We've seen some examples in the previous lecture, but maybe I wasn't as explicit about it as, for instance, the book is. The book has like a whole section on episodes. In the Bandit case, each interaction is one episode. That's just the terminology we use.
So in the maze, another maze, there's green thing. When we hit the wall, is that an episode, or when we hit the zero?
It's a very good question. So in the grid worlds we've seen so far, typically when you walk into a wall, we say that the episode continues. You just transition back to the same state you were. But when you go to the terminal state, we say the episode ends, and you get transitioned back to whatever your start state was. You could also have a start state distribution. Doesn't always have to be the same state. You could also think about, in practice, a lot of experiments say, for instance, with, if you think about a robot arm that tries to grasp something, what people tend to do in practice is they put the robot arm in some situation, and then it has to execute an episode in which it tries to grasp something. And then whether it's successful or not, the experimenter brings back the arm to its initial state, and then we start a new episode. So there's like a clear division there between one trajectory of experience, which is kind of continuous, and then there's a disconnect, and there's a new episode. What I said here is actually slightly more general. It doesn't just apply to episodes, but it also means within long episodes, temporal difference learning can already learn. And you can even learn when there's no episodes, when there's just a continuing system, because you can update from each and every transition. Okay, so there's now kind of an obvious question. How does this Monte Carlo method compare to temporal difference learning? What are the properties of these two? When should you use one? When should you use the other? So the goal, again, is still policy evaluation. We just want to evaluate this policy for a certain given policy pi. And one way to do that is to sample the return and to update a little bit towards that. And the other way is to use a one-step rollout, where I've now denoted this thing as the TD error, the temporal difference error, and update towards this one-step target. And to get a little bit of an intuition, there's an example here from the book. The situation is as follows. Somebody is driving home from work, and the initial state is that this person is leaving the office. The goal here is to estimate how long does it take to get home. In this case, we're not actually optimizing, so we don't have to put the time, we don't have to say, for instance, the time is negated, so that if you optimize time, you actually minimize the time. Instead, we're just going to predict how many minutes it takes, and each time we're just going to measure the amount of minutes already elapsed, and this will be a reward between each two states. And then we could look at the full reward summed over the whole episode, which starts at the office and ends when this person arrives home. Initially, there's some prediction, which is, at this case, 30 minutes. Maybe this is based on some past experience. So far, at the beginning, at the initial state, there hasn't been any reward, so there's no... There's basically no elapsed time. And the elapsed time is just the difference between the actual time that it took between each two states. Now the next state is when this person reaches the car, and this has been 5 minutes, which may not have been surprising, but when reaching the car, he also notices that it rains. And when it rains, typically it takes a little bit longer, so the prediction is updated to it's still 35 minutes now, even from the car. So the total time, total prediction is now 40 minutes from the beginning. Now a little bit later, things went better than expected, and we exit the highway. The elapsed total time now has been 20 minutes, so in some sense there's been a reward along the way of 15. And now we predict it's only 15 more minutes, because the highway went a bit faster than expected, say. Which means the total time has gone down a bit, to 35. But when exiting the highway, this person finds himself behind a truck, which is unexpected. So even though 30 minutes have already elapsed, it's still 10 more minutes expected to be before arriving home. And then finally, it even takes slightly longer than that, because after 10 minutes, we're entering the home street, but we're not home yet. And we expected 3 more minutes, and this turns out to be correct. This is just one sample trajectory where there's been some rewards along the way, which in each of these cases are basically the differences in elapsed time in that first column. Those are the rewards. And we see that the prediction along the way updated a number of times because of events that happened. Now we can understand the difference between Monte Carlo and TD from this example by looking at what the updates they would do. In the Monte Carlo case, on the left, there's this actual outcome of 33 minutes, and we would basically update the estimates from each state that we were in towards this. Now it should have been 43 minutes in total. So for this, we have to take into account what the elapsed time was. So essentially, we're only updating the values of each of these things towards the difference that we still need to get to 43. But each of them gets updated in exactly that way towards that number, so that the initial state, for instance, leaving the office, gets updated towards 43 now. Now, if instead you were doing temporal differencing, you get a different picture, because in each state we would see the actual reward, which is the elapsed time, and then we would just update towards the elapsed time plus the value in the next state. We're not discounting here for simplicity, which in this case means we're more updating like here on the right. Now, it might not be immediately obvious which one is better, but let me give you a personal example, anecdote from last year. I was going to one of these lecture halls, and I had been there a number of times already, but I thought I could take a shortcut, so I went somewhere inside a UCL building that I had never been in before. Got thoroughly lost. These are these interesting, mazy London buildings that you are probably familiar with. And at some point, I basically just gave up. And I found my way back to the exit, which was the way I came in. So I lost a little bit of time there just traversing this maze. But when I exited the building, I knew where I was again, so I knew how far it was to get to the lecture hall. Now, if I would have been doing Monte Carlo learning, that would have meant that at the point of exiting the building, I would have updated my estimate for how long it takes from the building to just this one sample of how long did it then take me to get to the lecture hall. Instead, if I would have been doing temporal difference learning, I could have bootstrapped on this very good estimate I had on exiting. So even, let's assume this didn't happen, but let's assume that on my way to the lecture hall, I may have been interrupted. Let's say I bump into somebody and I talk to them for a while. If I would have been using Monte Carlo learning, this would have been incorporated into the only sample that I've ever used to update my values inside the building that I've only been in once. Which is actually not a good thing to do in this case, because it's just a noisy estimate. It's much better, in this case, to bootstrap on the value of the well-known state that you've been in many times. And this is something that temporal difference methods can do. So there's pros and cons. But, and there's more than there are on these slides. We'll discuss more. But as I said before, one of the important differences is that temporal difference learning can learn before knowing the final outcome. And it can also learn without knowing the final outcome in a fully continuing case. So in temporal difference learning, you would update after every step, which means that even if in the same episode you come back to the same state, this might have been updated already and you might act differently, which is definitely a benefit. The other caveat all the way at the bottom that I wanted to just explicitly call out here is that Monte Carlo only works for episodic terminating environments, which is like, this is the hard constraint in some sense, but there's a softer version of this that it works better if you have maybe shorter episodes, because it just means you get more data. If you have very long episodes, this means that you'll have very few data points in a sense. This can also be understood as there being a Biasvariance trade-off, where, as in the example that I gave, this one rollout from a state can be quite noisy. And if you want to update towards that, that might be the wrong thing to do. And one way to just say that formally is that it has a high variance, this return. Now the temporal difference target which may or may not have been obvious, is a biased estimate. It's not unbiased for the actual value because we're bootstrapping. But the variance is much lower because there's only one action, one transition that we're depending on to get the sample, whereas in the Monte Carlo case, we have all of these transitions and we're using all of them to get our sample. And we can understand that by looking at a very simple problem. In this case, a random walk. So the start state here is state C in the middle. And there's essentially there's two actions go left or right. But you can also understand this as a Markov reward process without any actions, where you just randomly transition left or right. And then we can still ask the question, what is the value of each state? We're going to do this tabular, so we'll just have a separate value for each of these states, and we're going to update these. The reward structure is very simple. There's a 0 reward basically everywhere, except if you terminate on the right-hand side, then you get a reward of 1. Let's say we initialize the values to all be 0.5 at the beginning, a half, which is a fairly good estimate, because on average they will be, because half of the time you'll exit with a 0, and half of the time you'll exit with a 1. But for the individual states, of course, it's wrong, except for state C, where it is actually a half. Turns out the actual values are actually I think from the left to the right is 1 over the number of states, and then 2 over the number of states, 3 over the number of states. No, that can't be right because you don't get a half. So it must be 3 over 6 for C. The initial values here are denoted here as a straight line. The 0 next to the straight line means this is after 0 episodes. Then we've done 1 episode, randomly. And it just so happens to be the case, this is episode terminated on the left. And what we see is that the value as updated with TD has updated, and there's now a slight hinge in the line that points down all the way at the left. Note that the rest of the line is still flat. It's not that clear from this picture because there's other lines in here, but the rest of the line that corresponds to this 1 is still flat. We haven't updated any of the other states because we're doing TD learning, and they've all been bootstrapping. So the value of state C got a reward of 0 and then went to state B, say, but the value of state B was also a half. So the value of a half got updated towards a half, still a half. So it didn't update. There was a question?
I think you answered it.
Okay. Now we can continue and continue, and at some point after 10 episodes in blue, we'll see that the line is starting to shift, and after 100 episodes, it's pretty close to the diagonal line, which denotes the true values. In this case, it was run with a fixed step size, and this means we'll never actually converge to the true line. If you would decay the step size, as you do when you average, then it would actually go all the way to the straight line. But now we can do, of course, the same thing. We could run this on the same problem. We could run the Monte Carlo algorithm, and we did. There's a different picture in the book. I decided to run this one myself as well because I wanted to show you what happens when you tune the step size and also have a wider range of step sizes for both of these methods. Now there's shades of color here. I don't know how clear they are. They seem to be relatively okay. They go from light, which is a high step size, to dark, which is a low step size. And you'll notice that in both of the cases, the darkest line in black tends to be near the top, and the yellow line also tends to be near the top, which shows that intermediate step sizes tend to be better. This is in general true, as long as you have a wide enough range. There tends to be a U-shaped form, or if you want to optimize rather than minimize, it's an inverted U, for what your best step size is. In this case, we didn't decay the step size. We just kept a fixed step size for both of these methods. Yes?
Actually, if you go to the previous slide, please.
Mm-hmm.
The first situation, first episode, that value of A was broken down by whatever. How is that calculated?
Yeah, it's a good question. So how do we actually calculate that point there with the 1? Yeah, let's step through that more explicitly. So the update here is the TD update. So we have a previous value, which is a half, and we're going to update by adding step size times the target minus this current value. The target minus the value being the TD error. And the step size here was picked to be 0.1, which means that we're actually moving exactly 10% towards 0 here. That's how much it dropped. So it must have been 0.45 here. because the target in this case will be a reward of 0 plus the value of the next state, but the value of the terminal state is always defined to be 0 because you can never get any more rewards. So the target here will be exactly 0. If we would have exited at the other end, it would have gone 10% up towards 1, which is, well, somewhere here, I guess, because there you would have gotten a reward of 1 and still the next state would have been worth nothing. In later steps, we'll actually update towards values that are more and more different, so there will be these intermediate updates as well. I didn't explicitly put the algorithm on the slide. So the step size here is, this one is also described in the book, but essentially in this slide we discuss a number of different step sizes, including in orange, the one at the bottom there kind of going down quite quickly. That's the step size of 0.1 used for the previous figure. And there's a couple of things I want to point out from this graph. One is that the best TD methods do better than the best Monte Carlo methods for this specific setup. But for each of these, it holds that the dark one is at the top. This is the lowest step size, but it's very smooth and it tends to go down quite well. This is just a step size that tends to be maybe a little bit too small for how long we've run it. If we would run it longer, eventually it would go down and down, and it would go to very good performance. But if you only had 100 episodes in this case, you should have used a bigger step size to get there faster. But if your step size is too big, for instance, look at the yellow curve in both of these cases, it stabilizes at a higher error because you keep on updating and we're not decaying the step size, which means that we get irreducible noise in our updates. And one thing to note here is that the noise in the Monte Carlo returns is bigger than the noise in the temporal difference returns. The variance here is higher. We have a little bit of bias in the temporal difference case, but the bias reduces over time because our values get more and more accurate, which means asymptotically it'll actually reach the true values. Both of these do. But the temporal difference case, the bias is only transient and the variance is lower, which means that for certain step sizes like 0.1, it just does a lot better. It still doesn't go all the way to 0, the error, for any of these step sizes, because we still have the irreducible noise related to the stochastic updates. For the error to go completely to 0, we would have to decay the step size all the way to 0 slowly as well. Just to be completely clear what's on the curve here, this is the root mean squared error over all of the states. So if it would be 0, that means we have all of the state values estimated exactly right. Any questions? Okay. Now there's other differences between Monte Carlo and temporal difference learning. And this one especially may not be immediately obvious. The Biasvariance, I think, is fairly intuitive if you think about it. The Monte Carlo return is just noisier, so there's a higher variance, but it's unbiased. But there's also a difference that you can look at when you consider what happens if you only have a limited number of experiences. So in this case, we sampled K episodes, capital K episodes, each of which may have lasted a number of steps. So here, left to right means we're going through time in each episode, and then each row to the bottom will be another episode. And the idea here is that we're going to look at what these algorithms do if we only have a limited set of experience, and we repeatedly show the algorithms this experience, all the way until they're basically done learning, whatever much they can learn from this experience. And then it turns out the algorithms aren't equivalent. Even though both of them go to the same place, if you would have infinite experience and you appropriately decay your step size, if you have a finite amount of experience and you learn all that you can using these specific methods, they don't find the same answer. And to understand that, we'll look at a small example in which we have 8 episodes, and these episodes they're all only ever are in 2 different states, states A or B. There's no discounting. And turns out we only ever were in state A once. The first episode was we were in state A, we saw a reward of 0, we went to state B, then we saw a reward of 0, and then there was a termination. Second episode is we started off in state B, apparently, there was a reward of 1, and it terminates. And then there's a lot of similar episodes where sometimes the reward is 1, sometimes it's 0. Now the question is, what's the value of A and what's the value of B? Does anybody want to answer? Maybe let's start with the value of B. Who wants to make a guess? Yes. 0.75 is a good estimate here. We're just taking the sample average of all the rewards we've ever seen from state B. I think it's hard to do better than that. And now the next question is, what's the value of state A? 0 is one suggestion. Does anybody have a different suggestion? I hear some whispers, I don't hear any answers. So there's two basically valid answers here, in a sense. One is to say 0, because all the returns we've ever seen from state A have resulted in a total return of 0. That's, I assume that was the reasoning behind the answer of 0. But there's a different thing you could assume. Each time we were in state A, we transitioned to state B. But state B, we've estimated to be worth 0.75, because it's basically 6 over 8. But if each of the episodes that ever were in state A always went to state B, and we got a reward of 0 along the way, maybe this should be the same value. So 0.75. And it's not immediately clear which one of these is correct. Now, there's a way to characterize what these two different things are. And it turns out Monte Carlo and temporal difference methods go to these two different answers. The Monte Carlo answer will be 0, because Monte Carlo will just average all of the returns you've ever seen. In this example, the only return we've ever seen from state A was 0. So the Monte Carlo estimate will be 0. The temporal difference estimate won't be, because it turns out temporal difference learning in this batch setting, where we have a limited amount of data, but we replay that data over and over until we've learned all that we can, it turns out the temporal difference learning then converges to the solution of the maximum likelihood Markov model. Which means it basically finds the solution of the empirical Markov decision process, where all of the probability distributions are just the sample averages of the things that happened. In this case specifically, that means that the probability of ending up in state B from state A is estimated to be 1, because we've never ever seen an example where state A didn't go to state B. Also, the reward on that transition is estimated to be 0, because that's the only reward we ever saw from A to B. In that case, that means that the value of state A must be the same as the value of state B, which is 0.75. So this is kind of interesting. These two algorithms, if you just run them indefinitely on this data, they come up with different answers. Now, what does that mean in practice? Which one should you use? Well, the temporal difference learning algorithm you can interpret to exploit the sequentiality and the Markov property of the environment. It essentially builds this empirical model in a sense, without explicitly building it, but it finds the same answer. Monte Carlo doesn't exploit this property. It basically just says, I don't care how this thing is wired up. I'm just going to sample from each thing whatever happened in that case. I'm not going to use the fact that I know if one state came after the other, that these values are somehow related, perhaps. I'm just going to sample each of them as if they're independent. Now, this is a big potential benefit for temporal difference learning, especially if you're actually in the Markov decision process. Later on, we'll see that in some cases, this is maybe violated a little bit. For instance, because you do function approximation, so even if your state would be fully observable, you can't actually tell. But it's even clearer in the case where your state is partially observable. So you can't observe the full environment state. In that case, maybe it's wrong to assume this Markov property, and we'll see that sometimes it's better to go a little bit towards Monte Carlo. I say a little bit towards because there's actually algorithms that go in between these, which we'll cover in a later lecture. So here's a depiction of these algorithms schematically. So one way to understand the Monte Carlo backup is that there's this big tree of possibilities that of stuff that might happen, and we're going to update this value somewhere as a root of a subtree of this maybe bigger tree. We're going to update it towards the sampled return all the way towards the end. In the previous lecture, let me do that one first, we had dynamic programming, which went one step, but it looked at the full tree, which requires you to have the model to be able to build all of these things. Now, temporal difference learning does the intermediate version, where you only take one step, but we don't use a model, so we only ever have this one step. So we sample this, but then we do bootstrap, and we use a value estimate at each of these states. This is akin to using heuristic values when you do search. The using of these values along the way we call bootstrapping, which involves updating towards an estimate, which is not just an estimate because it's noisy, but it's an estimate because it's, for instance, a parametric function that's estimating the state value. Now, Monte Carlo does not bootstrap, which is an advantage in some cases and a disadvantage in others. And dynamic programming and TD both bootstrap. In terms of the sampling, Monte Carlo obviously samples, temporal difference learning doesn't sample, and TD, as said before, bootstraps and samples. And these are the main distinctions between these methods. And you can depict that a little bit like this, where the exhaustive search is all the way here at the top right. We haven't really covered that much. But it would be if you don't do the dynamic programming thing, but you just build your full tree, if you could, for a problem, and you search all the way towards all the leaves, and then you back up everything. Dynamic programming doesn't do that. It takes one step, but it does use the full model. And the other dimension is whether you sample or not. So exhaustive search is often not used, and instead typically we use Monte Carlo methods these days because we're interested in problems with huge search trees, in which case you just can't do the exhaustive search. For instance, the game of Go is a good example of this, where there's this huge branching factor and you can't do exhaustive search. Similarly, then in dynamic programming, you could view temporal difference learning as the sampled version of dynamic programming, or you could view it as the bootstrapping version of Monte Carlo. And all of these are valid. And turns out there's actually also algorithms in the intermediate here. And as I said, we'll discuss them later, but we'll leave that for future lectures. Okay. So now I want to move towards ModelFree Control. So what we've discussed so far was all estimation. We're all doing prediction. We're estimating these state values. But of course, we want to eventually use these things to get a better policy, to make you aware, or as a warning, depending on how you want to interpret it. Some of the material that we're covering right now is also what you'll need to understand in order to do the second reinforcement learning assignment. So that might be just useful to know. But first, we're going to do a refresher, which is something we've just talked about last lecture, which is the idea of policy iteration. The slide here says generalized policy iteration. This is what we kind of talked about, which is the idea of doing this interleaved process of estimating the value of a policy and then improving that policy. It's called generalized policy iteration rather than just policy iteration when you basically approximate either or both of these steps. So we don't necessarily fully evaluate a policy and we don't necessarily fully improve it. But if you do a little bit of both, or a little bit of either of these and maybe fully the other one, then it's a case of generalized policy iteration. And the idea here was that if you follow this process and you keep on improving your policy, eventually you'll end up with the optimal policy in the fully tabular case. Okay. So this is just a refresher from what we discussed last time. But we're going to apply this idea of policy iteration now in the setting that we're in right now. And first we're going to discuss the Monte Carlo case. So what we'll do right now is we'll take Monte Carlo as a policy evaluation algorithm, and we're going to use that to also improve our policy. In case you just came in, you haven't really missed anything yet, so don't worry. So remember, we're just using Monte Carlo. We have a return in expectation. This is equal to the true value. so that we can use this to evaluate a policy. And then we can improve our policy. However, there's a small immediate bump that we hit. Because what we did before is we wanted to greedify, but we were using one-step rollout of your model, which we don't have here. Fortunately, there's also a fairly easy fix. If we just estimate action values rather than state values, we can just maximize immediately, and it's much easier. We don't need a model. So this points to something that we'll see quite often, is that when you do control, people much more typically estimate state action values than they do state values, because it's much easier to get a policy out of it. You just maximize just the action values. So there's now an obvious thing to do, which is we do use Monte Carlo policy evaluation to estimate the action values. We don't need to go all the way because we do generalized policy iteration. We don't need to fully estimate it, but we just improve our estimates a little bit with policy evaluation. And then maybe we greedify. But that's probably not a good idea, because then we're not exploring. And this is something that we've discussed in the second lecture at depth. You need to balance exploration and exploitation. And this is especially true when you do Monte Carlo methods, because we don't have the full model. So if you never go anywhere, you won't learn about it. You need to explore to learn about the world. Fortunately, again, there's a fairly easy solution. Maybe we just explore a little bit, for instance, with Epsilon greedy. And turns out the generalized policy iteration idea still applies. You don't have to go fully greedy. It's enough to be greedier with respect to your current values than you used to be. Now, if you have an epsilon greedy algorithm and you estimate its policy and you get a new value out of that, if you then become epsilon greedy even with the same epsilon towards these new values, it is still a policy improvement step. And you can still show that this is a valid thing to do. There's a short derivation in the book that shows you that this will converge in that sense to epsilon optimal policies if you keep your epsilon fixed. Now, if we want to become truly optimal, we need to decay the exploration eventually. And the acronym GLI is quite often used in the literature, which is short for greedy in the limits with infinite exploration. And what this essentially means, formally in the tabular case, is that we're going to explore in such a way that we're going to try each action in every state infinite times in the indefinite future. It doesn't say anything about the ratios. You might try certain actions way more often than others, but in the long run you have to really try everything infinitely long, because we're going to average, we're sampling, so you can't have like complete guarantees of optimality without seeing everything infinitely often. This is the infinite exploration part. The greedy in the limit means that eventually you're going to be greedy. And one simple example of an algorithm that does that is to do epsilon greedy exploration with an epsilon that decays, for instance, with 1 over k, where k is the number of episodes you've seen. You could also use 1 over t or something like that, if you don't want to count episodes but rather count time steps. And this turns out to be sufficient to get you these properties, and this means that algorithms that, for instance, the Monte Carlo policy evaluation thing will eventually converge to the optimal values. So the algorithm is then very simple in some sense, because we're doing everything fully tabular. We just sample an episode. We're just going to do the fully episodic case. We're doing Monte Carlo. So everything breaks up into episodes, also only applies in episodes. We're going to increment the counter for each of the actions that we've seen, and we're going to update the value for that action towards the return. For simplicity, I'm not talking about what happens when you are in the same state multiple times in an episode. There's more about that in the book. For simplicity, you could just assume maybe each state and action in the trajectory is unique. Then you don't have any issues. You just average, you bump into most ones in that episode. And then we improve the policy by decaying the epsilon maybe a little bit, 1 over k. And then we pick a new epsilon greedy policy with respect to our current Q value estimates after this episode. Now there's a theorem that if you use this, the epsilon choice here guarantees that it's GLI, greedy in the limit with infinite exploration. then the Monte Carlo control algorithm depicted here will converge in the limit to the optimal action values, which means that if you have those, you can easily pick the optimal policy by just acting greedily with respect to those action values. So this is quite cool. We can get the optimal solution. But maybe we want to, so there's maybe a slight catch here in the sense of the normal Monte Carlo catch, that this can take a while. Maybe you need many episodes, maybe the episodes are long, maybe there's a lot of noise. So maybe we want to use temporal difference learning again. It has a lower variance. You can learn online, you can learn from incomplete sequences. You could also learn if there really are no episodes, if there's just this one continuing stream of data, life. So a natural idea is to use temporal difference learning instead of Monte Carlo for control, which is just to apply temporal difference learning to this Q estimate, and maybe to use epsilon greedy whenever. Whenever you are in a certain state, you just check your current estimates and you're epsilon greedy with respect to that. But you might update your estimates every time step. There's a natural extension of the TD algorithm that we already saw for state values, which just applies exactly the same idea to state action pairs. So we have a state action pair at the top. We have a transition. We see a reward in the next state. And then we also consider the next action according to our current policy, whatever that is. And this gives us an update that looks a lot like the update we had before for state values. In fact, it's exactly the same, except that we've replaced each occurrence of a state with a state action pair. This is called, because of the way these letters spell out that word, SARSA. State action reward, state action, SARSA. Yes?
I may be confused, but the epsilon just looks like a different greedy rate, like a learning rate is. And it's not clear that that means you can explore in different directions, because you're always in the greedy direction.
Sorry, yeah, let's clarify epsilon greedy again. So the question was, how does this explore in different directions if you use something like epsilon greedy? So epsilon greedy is a very basic exploration method. And just to recap what it does, it picks the greedy action with a probability of 1 minus epsilon, and it picks uniformly random across all of the other actions with probability epsilon. So it'll indefinitely try everything from every state, but it does it in a way that is sometimes called jittering. It doesn't like direct it go somewhere, it just tries an action and then maybe it tries the opposite action the next step. This could happen. In some sense, this is maybe the simplest exploration algorithm that you could consider. Okay, so we have the SARSA algorithm now with a step size. Make small steps because we're sampling. And then we could do generalized policy iteration again, where we use SARSA as a TD method to improve our estimates on each time step a little bit. We're not doing it on an episode by episode basis now. We're doing it on a time step by time step basis. And then we just continue to explore with epsilon greedy, with an epsilon greedy policy, which means we're doing epsilon greedy policy improvement. Each time the values change, we immediately adapt our policy to be epsilon greedy with respect to that policy, which is an improvement step over the value, the policy we were using before. This is the full algorithm. We just initialize some Q values. In this case, they are capitals because you could also interpret them to be just random variables if they're stored in a table. This is the convention used in the book. I mostly use the convention that the Q values are all small letters because it's a function, even if it's a table. But for the tabular case, you could basically use either, in a sense. And the algorithm just works by, for each episode, initializing some state from some state distribution. This is basically part of the MDP that picks some start state for you. Then you select an action according to the policy derived from your current estimates, for instance, epsilon greedy. And then you repeatedly update these values by taking a new action, observing a reward in the next state, also already choosing a next action in that next state. And then you can update and you assign the state and the action in order to make the loop well-defined. So you basically call S prime and you call A prime, or the other way around, sorry. And then you can repeat this loop. So the action is chosen, but then actually executed later, in a sense. We already pick it, we commit to it. Now what this algorithm does, it learns on policy. And this is an important distinction that we're going to make right now. On policy learning means we're learning the value of the current policy. This is the typical case in policy iteration where you want to estimate the value of the current policy and then basically in a separate step you improve maybe that policy. In the case of Sarsa, these steps are interleaved at a very fine grain on a step-by-step basis, but we're still on each step learning about a certain policy. In fact, you can, and people have many times, you can use Sarsa to just do policy evaluation. To have a certain policy, you just act according to it, but maybe for some reason you're interested in the policy, in the value of that policy, and maybe also for some reason you're interested in the action values of the policy rather than the state value, but maybe not necessarily to do control. You could do that, and then you would learn the value of that policy. The opposite of this, or like the inverse of this in some sense, is off-policy learning. Off-policy learning means learning about any policy other than the one you're following. So there's now a new notation here. We're still using pi to denote the policy that we're learning about, which is in both of these cases the same. But there's a new notation b, which is our behavior policy, which may or may not be the same as the target policy pi. I'll get back to that, but before I do, let's go back to the dynamic programming ideas from the previous lecture. Sorry, there's a slight mistake on the slide. I'll fix that before I upload. The pi here should be a k and the star here should be a k because these are the updates, not the definitions. So the first one is just policy evaluation with dynamic programming. The second one is what we call value iteration, which, as we discussed in the previous lecture, is policy iteration where you each time greedify after doing exactly one update to all of the state values potentially. And the bottom two are just the action value equivalent versions of the first two, where in this case I fortunately did denote them correctly with the bootstrapping on the value at the previous iteration. Now there's analogous TD algorithms. The first one we discussed, where again this should be a T. And again in the action value case it's correct. And we can now see that we already discussed two of these. We discussed TD learning and we've discussed Sarsa. By the way, TD learning is often used to refer to all of these, but people also use TD to only specifically refer to the top one. Where we just sample a state. So we have a step size to be able to smooth out the noise, and we don't need a model. But we could also sample basically the bottom one at the bottom here, which is value iteration, which is trying to do something else. These two are evaluating a policy. This one corresponds to TD learning, this one corresponds to Sarsa. But what does this one then correspond to? And it's an algorithm called Q-learning. And before I talk more about Q-learning, note that there were 4 equations. Here's the 4th one. There's no trivial analogous version of that one. Can someone say why? I'll go back to the previous slide because that might make it clearer. So the only one we don't have a version of is this one. Now what's different for this one compared to the other ones?
The optimal value. You can't sample it?
Yes. You can't sample it because the max is on the outside of the expectation. That's the main difficulty. Now obviously there's ways to then maybe approximate that, but it's less trivial. This is why I said on the next slide there's no trivial way to extend it. All the other ones you can directly sample. They're expectations of something. You don't particularly care maybe what, we can just sample. This one's harder because there's a max outside of the expectation. In fact, if you would sample this thing on the inside, you can't do the max over the actions anymore because you only have it for one action. Okay. Now, as I said, off-policy learning is about evaluating some target policy while following a different behavior policy. And this is important because sometimes we want to learn from data that exists already, but we want to learn what would happen if we would execute a different policy. For instance, we might have data by observing, say, humans or other agents. They would generate some trajectories of data, but we might not necessarily be interested in evaluating what they did. We might be interested to learn what would happen if we would have done something different. And this is possible if you do off-policy learning. Also, you could reuse experience from old policies if you do off-policy learning. Let's say you store these experiences, you could replay them. And then you could still learn from them if you can learn off-policy, because your current policy might be different. The thing we're going to talk about next is you can learn about the optimal policy while performing an exploratory policy. And in addition, you can actually learn about multiple policies, if you want, while following one. Now, Q-learning can now be understood as estimating the value of the greedy policy, because there's this max operator here. Note that this thing was conditioned in the value iteration case on a state and an action, ST and AT, which means that the reward and the next state are basically already conditioned on that action. So it doesn't really matter which policy you were following in state ST, because you will just update the appropriate action value anyway. But at the next state, we need to consider a policy. And in this case, we consider the greedy policy, which means that this will learn about the greedy policy, even if you don't follow it. And that's very nice, because it means that Q-learning will converge to the optimal state action value function as long as we basically explore indefinitely. But we no longer have to be glee. We no longer have to become greedy in the limit. In fact, we don't need to explore at all in some sense if we just have a data set in which all of the states and actions are tried infinitely often, which is maybe generated while you sample from it. It doesn't really matter how it was generated, as long as everything's in there often enough, Q-learning can find the optimal action value functions. So in some sense, we're decoupling the thing we're learning about, which is the optimal value, from the thing that we're doing, which is the behavior. Now, this is a practical example for what that then means, also from the book, where there's a simple grid worldish setup, and it works as follows. You start in the state S, there at the bottom left, and you can just do your typical grid worldish actions around. But whenever you fall into this region denoted the cliff, your episode will terminate. You will start a new episode in state S again, but you will get a reward of -100. Because it hurts. You don't want to do that. And on each of the other steps, you get a reward of -1, which means you do want to terminate. You do want your episode to end, but you just don't want it to end in the cliff. You want it to end at the goal, because then the hurting stops. Now there's an optimal policy here, which is just to step up once, then walk all the way across the cliff, and then go down into the goal. And in fact, this is what Q-learning will learn. It will learn the values so that if you are greedy with respect to those values, it will follow exactly that path. But now let's assume that we're not actually following that greedy policy. Instead, we're following an exploratory policy, an epsilon greedy policy, with a certain epsilon. I think in this case it was 0.1. In that case, Q-learning will still learn that this is the best thing to do, and with a probability of 1 minus epsilon, for instance, it will try to move across, on each step with 1 minus epsilon, try to move across the cliff. But on each step along the edge, there's an epsilon probability of selecting a random action, and one of these actions is down, which means it might just fall off of the cliff. The algorithm is in some sense blissfully unaware. It doesn't necessarily care because its goal is to find the value of the greedy policy. So whenever you select a non-greedy action, it doesn't particularly care. It will update the value of that action and it'll note, oh, that's a bad idea. But it's estimating the values for if you wouldn't be doing that. Conversely, SARSA is an on-policy algorithm, and it's actually estimating the value of the actual policy you're following, including the epsilon exploration. Now, it turns out, if you then run that algorithm, and then at the end, you look at what's the greedy policy with respect to the action values that Sarsa found, it turns out to go up a little further, and then walk all the way towards the goal, and then go down again, basically leaving a safety buffer between itself and the cliff. This is because the learning algorithm is aware of the exploration that's happening while it's learning. The action values capture the fact that you might take an epsilon action that sometimes steps down, and therefore the action values will be lower near the cliff. So the greedy policy learned by Sarsa in the end will walk further away from the cliff. Sometimes this is a good thing, sometimes this is a bad thing. Sometimes you want to find the policy that traverses this very narrow path. Sometimes you want a policy that's more robust to the exploration that might be happening. But this is a clear distinction. The graph at the bottom shows the reward per episode while you're exploring, while you're doing the epsilon greedy policy, and Q-learning is notably worse in that case. However, if you just evaluate the policy that they found in the end by taking the action values at the end of learning and then doing the greedy policy with respect to those, Q-learning will be better because it's found a shorter path. So it depends what you're after, whether you want to find the optimal policy or whether you want to find a policy that's robust to the exploration that you're using. Note also that in some cases, Q-learning might not reach the goal that often in this case because it tends to fall in the cliff a lot, which also might hurt learning or learning speed in some cases because it might just take you very long to get somewhere because the algorithm doesn't take the safe route. So these things might also impact the learning dynamics. Okay. We're going to shift yet again, so feel free to stop me if you have questions about Q-learning. And Sarsa. Also, of course, as always, if you have questions later, please let us know. For instance, on Moodle, others might have the same questions, and it's very helpful to get these questions as well because it makes me understand what is and what isn't clear, and maybe I can then be clearer next time around. I wanted to talk about an issue with classical Q-learning, and by doing so, I wanted to make it a little bit more explicit what Q-learning is doing. We're bootstrapping on the maximum action in the next state. I pulled out this term from the Q-learning algorithm, and I basically just expanded it here. Didn't do anything else. This is an equality. I just expanded it into saying, what does this actually mean? Well, what this means is we're actually evaluating, with our current estimate, in the state at t+1, we're evaluating the greedy policy, that's what this part means, in that state. We're taking the maximal action, maximally valued action, according to the same estimates in that next state. That's our policy that we're considering. This is our target policy, not necessarily our behavior policy. But this means we're using the same values, Qt, the same estimates, to both select and evaluate an action. But these values are approximate. They're noisy because we sampled to learn them. We're also bootstrapping. We might be doing function approximation later on. There's many reasons why these values might be a little bit off. But if they're approximate, then actually this means that in general we're more likely to select overestimated values with this argmax than we are to select underestimated values. So if we're more likely to select an overestimated value and then we use the same values to evaluate that action, it'll look good. One way to think about this is if you have many different values, just abstract away states, actions, and everything else. Just think about having 10 different estimates for 10 different equal Gaussian distributions. Some of these estimates will be low, some of these will be high. Let's say the actual mean is 0 in all cases. If you just have finite sample averages for each of them, some will be a little bit below 0, some will be a little bit above 0. But if you take the max, it will typically be above 0, even though the actual mean is 0. That's what's happening here. And this causes an upward bias. Now there's a way around that, which is to decouple the selection of the action from the evaluation thereof. One way to do that is to store two action value functions. Let's say q and q prime. And if you do that, then we can use one to select, in this case q to select an action, and we use the other one, q prime, to evaluate it. What this is essentially doing is we're saying we're using the policy that is greedy with respect to this one Q function, Q, and we're evaluating with the other Q function, Q prime. Or we could do the inverse of this, where we pick the policy according to the other one. But each time we select according to one and we evaluate with the other. And then what we could do to make sure these things are actually distinct estimates of the same thing is to randomly pick one whenever we do an update. We just update one of these action values for each experience. So they have disjoint sets of experiences that they're learning from. This is very akin to cross-validation, where we basically split up the data into two folds in a sense. And the overestimation bias is also akin to the problem that cross-validation is trying to solve, where we're trying to solve the over-optimistic guess that we might get if you would just validate yourself on your train set.
Is there a limit to how many Qs you could stack up for better performance? So would you do triple Q learning?
It's a good question. Do you need to go double Q learning? Could you do triple Q learning? Many more fold Q learning? I have investigated this in the past. I looked at things like 5-fold and 10-fold Q learning. And this is a couple of years ago, so I forget what the exact results are. I think somebody else followed up on this as well with a different paper. And there might be a trade-off there. There's different ways also to do this, because you could imagine if you have many folds, do you use many to select and then one to evaluate, or the other way around? Do you use maybe one to select and then many to evaluate? It's not immediately clear which one is better. So there's a couple of design choices there. So in short, the answer is you can definitely do that. Whether it's better or worse is unclear. And maybe it also depends on the domain.
And is it the same as, like, would you get the same Q functions if you just did two separate simulations and each time just updated them based on their simulation?
So can you do something similar where you just basically have two Q-learning algorithms, each in a separate simulation? Is that the question? And the answer is no. You have to have this interleaving where they know about each other. If you would just do Q-learning in two separate simulations, you would get two overestimated estimates. So you need to do this where you take the max, essentially. Good questions. Thanks. By the way, just one thing to note. We're splitting up the experience to learn about these two state action values. But that doesn't mean we're necessarily less efficient in terms of how good our estimates are, because when we want to act, say how good our policy is, when we want to act, we can just combine them. At the bottom there I said you can add them together. That's okay for acting. If you want a good prediction, of course, you should just average them rather than adding them together. But if you're only interested in picking an action according to them, you can just add them together. So the behavior here can be different from what we're using here to estimate. We're estimating two different policies. One is greedy with respect to one, and one is greedy with respect to the other action value. But we can act according to a combination of these, and that's perfectly fine because we're doing off-policy learning. Now, does this work? Is this a good idea? So this is an example. I guess I could have just put this one thing. I used to have this slide first show one and then the other, but it's a bit of redundancy now. This is in a roulette case. There's a single state. There's a lot of actions that basically go back to that state. Because you're at a roulette table is the setting. The agent's at a roulette table. There's many different gambling actions. There's like 170 approximately. And in actuality, all of these gambling actions have an expected slightly negative reward, but they're very noisy. Each time you can continue betting. For simplicity, let's say there's no state. So you can never go bankrupt. But maybe you can leave the table. Maybe there's also an action that just quits, which would terminate your episode, and this is the optimal action to take. Because you would stop gambling, you would stop losing money. Now what happens if you run Q-learning? The overestimation is so large that if you do a synchronous Q-learning update on all of the actions at the same time, and you do 100,000 of these, so in total you'll have done 17 million updates to a tabular setting with just one state, there's an overestimation of more than $20. Even though we're betting a single dollar on each step, which means the expected return is actually like -5 cents. So more than 20 is way off, is unrealistically far off. You'll very rarely get more than $20 from betting a single dollar. Now, of course, this is the long-term return. I think the discount is probably 0.9 or something like that, or 0.99. I don't remember. But still, it's unrealistically high, and it's also positive, which is wrong, because it means that the optimal policy is to leave the table, but this algorithm will estimate that it's much, much better to stay at the table and keep on betting. Conversely, if you use the double Q-learning algorithm from the previous slide, you'll actually find that it very nicely estimates something very, very close to the actual value, and it would also learn to leave the table. You can make this more extreme by even paying the agent, for instance, $10 to leave the table. Q-learning would still keep on gambling. Double Q-learning would very quickly take the money and run. This is a slightly contrived example because there's only one state and it's deliberately very noisy just to show this. So you could question, does this actually happen a lot in practice? So one thing we did is there was a version of Q-learning that was used for the initial results on Atari with DQN. This got some scores on games which were quite good and people were fairly excited about this. But then turns out if you just plug in double Q-learning into that whole system, this whole agent with lots of bells and whistles, but you just replace the Q-learning update inside there with double Q-learning, you get the blue scores here compared to the red scores that DQN got. And indeed, not showing that here, but you could show that in many of the games there were very clear, unrealistic overestimations of the values. So this does happen in practice. Interestingly, the Atari games that this is run on are deterministic. So in that case, the overestimations didn't come from the noise in the environment, they came from your approximation errors and the noise in the policy that updates these. Your values would still be approximate, and still taking a max over these would cause overestimations. The differences here were much bigger than I expected them to be, by the way. So why are there some games in which it does worse? Yeah. A lot of this is just random. And in some cases, there's maybe a slightly more precise answer as well. In some cases, like these things will go up and down a little bit if you run it again, because these take a lot of, or not as much these days anymore, but it used to take quite a bit of compute and time therefore to run. So we couldn't run that many repetitions of the experiment. But the other explanation is also that these algorithms will actually have different properties. And in some cases, the overestimations might actually be helpful in terms of the policy that they make you follow. They might steer you towards certain places that just happen to be good for that specific game. So even though in general it's bad, that doesn't mean it's always bad. It could be good. And that's what happens here maybe on tennis. We see this, by the way, much more often, especially in deep reinforcement learning. Here, deep networks were combined with reinforcement learning. What very often happens is that if we have an improvement in terms of algorithm, many, many games get better and a few get worse. This is generally the case because these games are fairly specific, and some games will just basically have worked well for other reasons than the algorithm being good. Or they may have exploited, in some sense, a flaw in the algorithm to still get better policies in the end. So in some sense, the way to look at these things is not to look too much at the score for each game, but to more look at the general trend. Yes?
What's not quite clear to me is why we don't, over time, unlearn the overestimates when we get more samples.
Very good question. Why do the overestimations stick? Why don't we unlearn them? Actually, we do unlearn them. Q-learning, in this case, this is a tabular setup, is guaranteed to find the optimal Q values. What I didn't say is how quickly. This line that seems to be plateauing here is still going down. And eventually, this was run with a decaying step size, and eventually it would find the optimal solution. But if I gave it 17 million updates already, and it's this far along, that's probably a problem. So the answer is yes, Q-learning is sound theoretically, and it will find the optimal policy. There's just ways you can improve this in practice. By the way, double Q-learning is guaranteed under the same conditions as Q-learning to also find the optimal policy. In this case, it just goes there much faster. Yes?
Is there a mathematical way to calculate when Q-learning would reach its optimal state, like when it would be very close to a value?
So the question is essentially, what's the convergence rate of Q-learning and how can you reason about that? There's definitely been some work on this, mostly for the tabular case. in which people have shown basically how quickly Q-learning converges, and this depends on many things, as you might expect, but the most important things are your behavior policy, also the structure of the MDP, whether the MDP itself is connected in a sense that you can easily cover all of it, and also, very importantly, on the step size that you pick. Because you can't do, because of the bootstrapping, you can't do the flat averaging that we were doing for Monte Carlo. You need to do something else, because the thing we're using to estimate our optimal value is changing because of two reasons. One is the values we're bootstrapping on, and the other one is the policy that we're following, which is kind of covered with the exploration. But if you can take account of all of these things, and then you can derive basically rates at which these things converge. And that's already for the tabular case quite complex. Especially for the DPRL case, basically nobody knows. Very good question, thanks. By the way, I'll be very happy to give concrete pointers to papers for people who are interested in these sort of things. Okay. So now we can, yes, we can quickly still cover the final topic of this lecture. And for this, this is still in the context of off-policy learning. We want to learn about a different policy than the one we're following. I gave you an example of an algorithm that does that. Q-learning estimates the value of the current greedy policy while following maybe something else. But we maybe want to do that more generally. And another way to think about what I'm going to explain next is a different way to come up with the Q-learning algorithm. But we'll also find actually a more general algorithm than that. So this is a very generic statement here. We want to estimate a certain quantity. X here is basically random. I probably should have made it a capital. And it's sampled according to some distribution D. Now we can just write this out. You could turn it into an integral if you prefer. In this case, I just made it a sum, so there's a finite number of elements x, and each of them have probability D of occurring. Now the expectation can then simply be written out as this sum, the weighted sum of fx for each x with the probability that it might occur. What we're actually interested in is something else. We're following a different distribution, we're sampling, from a different distribution, D prime, and we want to still estimate this thing, but using the samples from the other distribution. And for this we can use something called importance sampling, which reweights the distribution. And one way to see that is by simply multiplying and dividing by this D prime x, noting that this is again an expectation, but now it's an expectation with respect to the distribution D prime, which means we can write it again in expectation notation, but the fraction remains. Please make sure that you follow that part. So what this means, actually let me go to the next slide first, because first I'll just apply it to the reinforcement learning case. This is exactly the same as we had before. I just plugged in some familiar quantities. So now we're trying to estimate the expected reward, say. Let's just take the one-step reward for simplicity. Bandits, say. And we want to estimate this quantity, the expectation under a certain target policy pi. Now we can write that out as the weighted sum of the expected rewards given a state in action. These you can compute if you have the MDP from the distribution of the rewards. But this is just a definition. We say this is the expected reward conditioned on S and T, and then weighted by the probability of selecting that action A. We can do the same trick, multiply and divide by the probability of the behavior selecting that action, which is again an expectation. So we can write it out as an expectation, which means we're multiplying the reward with the probability of selecting the action according to the target policy, divided by the probability of selecting it under our behavior. This means that we can sample this thing at the bottom and get an unbiased estimate for the thing at the top. So that's what we'll do. We're following a certain behavior B. We'll sample this quantity, target policy divided by behavior policy times the reward, and it'll be an unbiased sample for the expected reward under the target policy. Now note, as a technicality, but it's an important one, that b of course can't be 0 for this to be valid, which has an intuitive explanation. You can't learn about behavior that you never do. So if you want to learn about a target policy that selects certain actions, you'll have to at least have a non-zero probability of selecting those actions yourself as well, and then everything's well defined. A different way to say that is that the support of the behavior distribution needs to cover at least the support of the target distribution. Now we can take this exact same idea and we can apply that to the sequential case, and it turns out there's more that can be said about this, but I'm just going to skip to the conclusion, which is it just means that you have to multiply all of these things together for all of the actions that you did along the trajectory. Let's say we had a trajectory up to time big T, then this product goes up to big T as before. So this is for a full episode. We're doing Monte Carlo. We're just multiplying together all of these ratios, and this turns out to exactly appropriately reweight the return to make it an unbiased estimate of the return under your target policy. So then we can just update towards that. Using our standard Monte Carlo algorithm, we update towards this target. There's no bias. This is an unbiased estimate for the true value of the target policy. However, it can dramatically increase variance. Now, what is a very simple way to see that? Well, let's assume that our target policy is actually a deterministic policy that deterministically selects a certain action in each state. And let's say our behavior policy is more random. It explores, for instance. If your episodes are long, that means that one of these pi's is very likely to be 0, which means your whole return will be replaced with a 0. However, there's a couple of episodes in which the return will be non-zero, but the probability of selecting exactly all of those actions may have been smaller than 1 for each of these. If your behavior, for instance, is epsilon greedy, then this b here at the bottom is at most 1 minus epsilon. Which means if you have a product of many of these, we're dividing 1 by 1 minus epsilon, which is a quantity higher than 1. And this is in the best case. In some cases, it will be epsilon. So we'll have 1 divided by epsilon, which is even higher, which means that this full product will be very big. What essentially is happening here is we're downweighing trajectories that the target policy would never do, all the way to 0 in this case. And we're upweighing the trajectories that the target policy would do, which are maybe very rare for the full trajectories. And turns out we're reweighting them in exactly such a way that on average we get the right answer. But if there's only a handful of episodes that ever really follow the full target policy, this is going to be very noisy. If your episodes are very long, these are going to be very noisy. Another way to say that, it has very high variance. Is that clear? So essentially what I'm saying here is maybe maybe bias is not the only thing to care about, even though it's unbiased, might not be ideal. There's maybe a now obvious thing you could do, which is to not use the full return. Instead, let's use TD. In that case, we only need to reweight with this one important sampling ratio if we estimate state values. Because we only need to reweight for the probability of selecting this one action according to the behavior policy rather than the target policy. This has a much lower variance because we don't have this big product of things that can be higher than 1. We only have one of them. Also means you can learn even if the policies are only similar for one step, rather than needing trajectories in which you just happen to pick the same action as the target policy on each and every step of them. So whenever you have a transition here within an episode in which these actions match, you can already start learning from that. So this is a much more efficient algorithm often. Now you can apply that same idea to action values, but turns out it's even simpler because we don't need to importance sample if we do the one step. The importance sampling is still important to try to wrap your head around, because it'll come back essentially when you do multiple steps in some cases. But for the one step, we can essentially just pick an action according to the behavior policy, but we're not just going to ignore that. And instead, we're going to reweigh the action values in the next state using the target policy. This quantity here, one way to understand it, let's assume for a moment that Q is a good estimate for the policy of the target policy. If that were the case, if you then would do a weighted sum according to the target policy, this quantity as a whole would indeed also be a good estimate for the state value of that policy. If that is the case, then Q would remain a good estimate for the target policy. So in some sense this is sound. But you can show that this is exactly also the right thing to do. That was the more intuitive explanation. And this algorithm is called expected sarsa, for the reason that you can also interpret this as being the expected update that sarsa does, which was just an on-policy TD algorithm, if you take the expectation with respect to the target policy of the action that you select in the next state. This defines the expectation because we're already conditioning on the state in the actions. They have the same noise, sarsa and expected sarsa, in terms of the next state and the reward, but we're already conditioning on the state in the action, so we don't need to correct for the policy for the policy for action AT, because we're already conditioned on that action. We're only ever updating the value of that action whenever we select that one. And turns out expected sarsa basically has the exact same bias as sarsa. The bias only comes from the fact that we have an approximation Q here, the typical TD bias, but it's a fully on-policy algorithm. So as long as the target policy matches your behavior policy. But it's a little bit more general than that, because if your behavior policy is different from your target policy, which is the case when B is not equal to pi, then we could call this generalized Q-learning. And a special case of this is then when this target policy is deterministic, so then you pick out one. And more specifically, if it's greedy, you get exactly Q-learning back. So this generalizes both, in some sense, both sarsa, which is the sampling-based version of this, as long as your behavior and your target are the same. It's fully on policy. And it generalizes Q-learning, where we're trying to estimate a different policy, in this case, the greedy policy. Now this is just taking those steps towards Q-learning, making that explicit. We pick our target policy to be greedy, and then turns out these expected updates, the expected sarsa update just becomes Q-learning, as I said on the previous slide. And again, Q-learning, you can just use whatever behavior policy you want, and it'll still estimate the value for the target policy, which in this case is the greedy policy with respect to your current values, as discussed before. So now we kind of came from importance sampling and we went and we got the Q-learning back, whereas previously we just sampled a value iteration update from dynamic programming and we also got Q-learning. And it's the same algorithm in both cases, but you can arrive at it in different ways. One is basically coming from the Monte Carlo side, and the other one's coming from the dynamic programming side. Okay, so you have a little bit of time left for questions if people have them. Please feel free to ask, because if you do have a question, you're very likely not the only one with that question. Okay, and otherwise, before I end, I just wanted to mention that there will be a new reinforcement learning assignment, which will come out over the weekend, and then you'll have a couple of weeks to, or Monday, I think Monday it says in the schedule. And then you'll have a couple of weeks to do all of these assignments, including the reading week, I think. There will be a little bit of a while before we get back to the reinforcement learning lectures. Next week there will be 2 deep learning lectures, and I think then there's reading week. And then the week after that we'll return and we'll talk about policy gradients and Temporal and everything. Thank you.